Welcome all. Today we are going to discuss about field bosons. Before discussing about field boson, we can have a quick look at what will happen when two particles come together in a molecule. So that if two particles come together in a molecule, there will be interaction, or can we say that there will be exchange of some particles which may lead to bonding, or some another characteristics of this particle which can make a difference in the property of the particle. So, the mutual force between two particles can be regarded as being transmitted by the exchange of other particles between them, which is a concept that is applicable to all fundamental particles in the universe. So, this concept applies to all fundamental interactions too. This concept, which is always applicable to all interaction, the particle exchange, which are also called bosons, are depicted in the table, so that the table is classified in the form of interaction, particle affected, range, relative strength, particle exchange, and role in the universe. As like the change in interaction, there will be change in the particle affected, so that the range may be different between the others. Strength varies and the particle exchanged will be different, which is always depend upon the interaction and the particle affected. We can see a quick look at this. If the interaction is strong, the particle affected will be of two kinds, quarks and hardons. The range will be up to a range of 10 raised to minus 15 meter, and the relative strength will be 1, and the particle exchanged will be gluons. In the terms of particle affected will be quarks, and if the particle affected will be hardons, the particle exchange will be mesons. Next interaction is the electromagnetic interaction. The particle affected is charged particles which have a range of infinity and a very low relative strength up to a 10 raised to minus 2 something, and particle exchange will be photons. Next two are the weak and the gravitational interaction. In case of weak interaction, particle affected will be quarks and leptons. It has a very small range of 10 raised to minus 18 meter, and relative strength will be 10 raised to minus 5, and the particle exchanged will be intermediate boson. Next is the gravitational field. Particle affected will be all, because the gravitational field, as we know, it is applicable to all systems in the universe. The range will be infinity, and the relative strength will be 10 raised to minus 39, which is the lowest strength in this group. Particle exchanged will be gravitons, and the role in universe assembles the matter into planets, stars, and galaxies. So without this gravitational field or force, nothing can exist in the galaxy. The graviton, which is the carrier of the gravitational field, the graviton should be massless and stable and have a spin of 2 and travel with the speed of light. Its zero mass can be inferred from the unlimited range of gravitational force. If energy needs to be conserved, the uncertainty principle requires that range of force be inversely proportional to the mass of particles being exchanged. Equation is given below, which is m pi approximately equal to h cut divided by rc. From this equation, we can interpret that if the energy needs to be conserved, uncertainty principle requires that the range of force be inversely proportional to the mass of particles exchanged. Hence, the gravitational interaction can have an infinitely long range only if the graviton mass is zero. The interaction of gravitation with matter should be quite feasible making it extremely hard to detect. So there is no direct experimental evidence either either for or against the existence of graviton. So we cannot confirm whether there is presence of graviton or not, either by experimental or by fundamental techniques. The carriers of weak interactions are called intermediate vector bosons, of which they are of two kinds. Because the weak interaction has a short range, mass of such particles are very large. One kind called W has a spin of 1 and a charge of plus or minus E is responsible for ordinary beta decays. Its mass is 85 times the proton mass, so that it's very much heavier than when we are looking up to a proton and this type of molecule. The other kind is Z, which also has a spin of 1 but is electrically neutral and heavier than W. It is approximately equal to 97 times the mass of proton, and its effects seem confirmed to certain high energy events. Both decay in 10 raised to minus 25 seconds. So it is very much unstable in nature. Although W particle is a natural concomitant of the weak interaction and was proposed many years ago, the idea of Z particle originated more recently in a theory that unites weak electromagnetic interaction, and its discovery helped confirm the theory. The connection between the weak and the electromagnetic interaction was independently developed in the 1960s by Steven Weinberg and Abdus Salam. The key problem to overcome the constructing theory was that carriers of weak force have mass, whereas the carriers of electromagnetic force, namely photons, are massless. What Weinberg and Salam did was to show that the certain primitive level both forces are aspects of a single interaction mediated by four massless bosons. Through a subtle process called spontaneous symmetry breaking, three of the boson acquired mass and become W and Z particle, with a consequent reduction in the range of what now happens as the weak part of total interaction. One way to look at the situation is to regard the mass of W and Z bosons as being attributes of state that happen to occupy rather than intrinsic attributes. The fourth electroweak boson, the photon, remained massless and the range of electromagnetic part of the total interaction accordingly stayed infinite. Since hadrons seem to be composed of quarks, the strong interaction between hadron should ultimately be traceable to an interaction between quarks. The particle that quarks exchange to produce this interaction are called gluons, of which eight of which are postulated. Gluons are massless and travel with the speed of light, and each one carries a color and anticolor. The emission or absorption of a gluon by quark changes the quark's color. For instance, a blue quark that emits a blue anti-gluon become a red quark, and a red quark that absorbs this gluon become a blue quark. Because gluons have a color change, they should be able to interact with another form of separate particles called glue balls, and thus the search for glue balls has thus far been fruitless. We can now show a computer reconstruction of the result of proton-antiproton collision in which a W boson was created. The UAA detector is outlined in the display. The W boson, one of the carriers of the weak force, was first identified in CERN in 1983. The figure is as shown. Thank you.